This paper was presented at the JCT Traffic Signals Symposium 2023 in Nottingham, thanks to the support of AGD Systems, INRIX, Message Maker Displays, PTV Group, Simplify Systems, Smart Micro UK and TRL Software.
Thank you very much. So, just going to talk about some work that we have, that I reported 12 months ago, starting off in Cambridge, around pedestrian optimisation within Cambridge city centre. But just a quick, for those that don't know, Starling, young company based in London, but doing a lot of good work elsewhere in France and Canada. We're specifically focused in on enabling pedestrian and cyclists and other types of pavement user safety without having a detrimental effect on the traffic. So I'm going to take you through this presentation. Dominik, there's going to be a lot of information and it's going to go at some speed. And there's also a lot of data that we can explain to anyone really interested in pedestrian optimization. So please come and talk to us. This is going to be fast and detailed, well, not too detailed. I'm just going to now hand over to Dan Clark from Greater Cambridge Partnership.
Thanks very much, Andrew. So I'm Dan Clark. I'm going to talk a little bit about the local context. So I work with local authorities. We have funding for one purpose, and that's to get people out of their private cars and onto more sustainable modes of transport. We've got a target of about 25% of journeys that are currently made by car to be made by walking, cycling and bus. There's huge investment at the moment in the bus network and also in the cycling network, and pedestrians are a bit of a forgotten kind of breed in that. This is all backed by policy, so if you look at our local transport plan and you look at national policy, obviously pedestrians are at the top of the sustainable transport pyramid, so we really ought to be doing more for them. Our ambition, say 25% modal shift, we really want to improve air quality, and obviously by encouraging walking we are also improving health outcomes, and it supports our pathway to net zero. We've declared a climate emergency, and we also have a sustainability strategy which looks at achieving net zero by 2045, which is slightly earlier than the national one, but also it's about creating better public realm. So at the moment, this is kind of how we treat pedestrians. We have very narrow pavements, we have areas of severe congestion at crossings, and so we need to do something differently, and that's why we've started working with Andrew and his team on a pilot to see how their technology can really support our ambition. And yes, it's important to improve the public realm, to improve pedestrians, but actually crossings are a significant pinch point, so we need to look at how we can operate them better.
Thank you very much, Dan. So our crossing is outside of the main entrance at Anglia University. It has sporadic high saturation of the sidewalks. One side of the road is very, very narrow, and the other side of the road is much wider by the university. But it is also on a walking corridor further down East Road, where students, as well as those that live around the area, because it's a highly residential area, use it. So I'm going to hand over to Dominik now to start talking about our process and our results.
Thank you. So the first step that we had to do is compare the existing sensors and our sensors against the ground truth. We used Momentum Transportation Consultancy for this, and we gave them a brief using the Topaz specs for on-crossing detection, curbside detection, and approaching vehicle detection. We gathered some comparative data over diverse weather conditions and light levels to make sure that we cover a wide range of different environmental conditions. The next 3 slides are going to show the results of this. We're not going to go into too much detail. There's just one thing to note, that there's about 5 to 10% of edge cases where we had actors on or near the boundaries of the detection zones. So the output may vary depending on the human judgment of the assessment. So the first one was the curbside detector. As you can see, we're roughly 10% more accurate than the existing sensors. And a big part of that is because our sensors can crosstalk. So we have two sensors on either side, and there's usually a blind spot underneath the traffic signal visor, which is also where the push button is located, so a lot of people tend to wait there. Our sensors can talk to each other and can tell the other sensor there's someone there or there isn't, which is why we generally tend to have less false negatives. The next slide is for the on-crossing detection. So you can see there's a significant number of false positives on the existing sensor. We analyzed the sample data, and a lot of them were edge cases where vehicles were just outside the boundaries. And it kind of makes sense. The on-crossing sensors have teardrop-shaped detection zone. It's a square, rectangular shape that we're trying to track. So most of them will fall into the may detect zone rather than the must detect zone. So overall, I think they're fine. And it's not generally a problem because the on-crossing is mainly used to extend the green period for the pedestrians. So if it picks up some vehicles while they drive, then generally not a big issue. And the last one was the approaching vehicles. Again, you can see there's a large number of false positives on the existing sensor. The problem with this was that the ground truth is obviously image-based, and the topaz spec for the above ground vehicle detection has a may detect zone of 35 to 60 meters. And within the images, it was just difficult to distinguish anything further than 35 meters. What we gathered from all of this information is that our sensors are at least as good as the existing sensors, and both technologies are good enough to operate a puffin crossing. And yeah, I'm going to hand off to Andrew.
So this was just a quick slide. The main thing was this year we went to the National Walking Summit where we held a workshop with the delegates. And it was interesting because they're not signal engineers, they're not road engineers, they're all active travel people or kind of those types of kind of people. And really these were the big things that they fed back to us around metrics associated with pedestrians, because what we were looking to do in terms of getting this metrics is what metrics do we need to capture that is as useful to us and for you guys as well as to other constituencies in the authorities.
Okay, when it comes to the metrics, we tried to stick with metrics that are very similar to traffic metrics. So it's counts, flows, speeds, densities, and as we've already mentioned, accumulated crosser delay. When it comes to the setup of these, there's a few things we need to know. We need to know what do we need. So we need pedestrian density, count, speeds, etc. Where do we get this from? So we need to define our zones that we're interested in, the detection zones, and how will we group the data together? There's multiple ways of doing it. You could do it cycle by cycle. You could get average, minimum, maximum over a certain period of time. It depends on the metrics. We've generally gathered data in 15-minute chunks, and then again, it depends if it's minimum, average, or maximum. So the next slide explains how these different metrics correlate to each other. So once we've gathered a bunch of metrics, we can start to look at them and see how they interact and how they correlate. In this slide, you can see at top left, this is the accumulated crosser delay over a period of 22 days. If we zoom into the 3-day period, at the beginning, you can see that there's a spike in accumulated crosser delay. If we compare that to the same day, the Fruin level, which is a measure of pedestrian comfort, and it's based on the amount of space that each pedestrian has. It's generally higher, which makes sense. People had to wait longer, so the density will be higher. And the amount of crossers, so the crosser count, is also increased. Again, makes sense. More people, higher delay, higher density. And all of this without any difference in the vehicle traffic. So, sorry. So, the next step was to think about the optimization of the crossing. So, once we know the behavior of the pedestrians around the crossing, we can start to think about how can we optimize for pedestrians and vehicle demand at the same time. For easy adoption and to make sure that we can use this in a wide variety of places, we have to use standard controller interfaces so that we can just interface with as many controllers as possible. Our aim is to try and intervene as little as possible. So basically only when the scenarios or the metrics are outside of a normal range. On reflection, after we've finished this phase of the trials, we came to the conclusion that we started out with a configuration that was a bit too sensitive, which meant we intervened quite a lot. We had to start somewhere, but the next step would be to fine-tune the configuration, try and minimize the amount we have to intervene while still keeping the output, the results at a maximum. We'll get into some details in a bit. So the generalized workflow of the optimizer, we have our Starling detector, which does detection and tracking. On top of that, we have user objectives and parameters, which really depends what do we want to optimize, what do we want to make better about the crossing. And both of these, so the metric data and the user objectives, feed into the optimizer, which then seizes any abnormal activity. If there isn't, we don't do anything. If there is, then we need to intervene and send signals to the controller to get it to do what we want it to do. So there's two types of interventions. There's the immediate and the predicted. For the immediate, we know, right, we've hit a critical threshold, so we need to intervene now, we need pedestrian green. Or there's a predicted, we predict that there's going to be some demand in the near future, so we suppress the current demand and call for the demand as soon as we need it, once we think it's the optimal time. So in the next two slides, we're going to show some example interventions and the metrics around them. And it's just to highlight roughly how it works. So the first graph, the approaching pedestrians, shows how many pedestrians are approaching from different directions at different times. The next graph below it shows the current waiting pedestrians, and you can see there's few people approaching, there's people waiting, and that increases. Part of that is because in our site, the main university entrance is from the side. We see down both roads, so we can't see everything. So the amount of pedestrians increases. In the bottom right, the optimizer output, you can see when the optimizer decides now the demand is required, it flips it. And in the crossing pedestrians, you can see shortly delayed after, the pedestrians get green and they start crossing. And then this is a predicted intervention. So in the approaching pedestrians, you can see there's a lot more people approaching from different directions at different times, highlighted by the different colors. There's fewer pedestrians waiting, but there's already some waiting, so the optimizer chooses to suppress the demand, hold off from switching to pedestrian green until we hit a critical threshold, at which point we switch, we set the demand, and you can see the crossing pedestrians shortly after start to appear. So the summary, as we said, we had quite a high number of interventions, a total of 3,872 interventions during the trial period. The results speak for themselves, though. We managed to reduce the accumulated crosser delay time by 38.1%. while only having a 4% reduction in crosser count. The maximum pedestrian density did increase, but we explain that by basically what the optimizer is trying to do is it's trying to platoon the incoming pedestrians, so the density will slightly increase, but the overall delay time will reduce. And interestingly, we also had a 6.5% reduction in near-miss incidents between pedestrians and vehicles. Yeah, I'll hand off to Andrew again.
So in summary, what we were doing is enabling Cambridgeshire to answer some of their policy decisions around creating a better facility that was more responsive to excessive demand at this crossing, with the view that this could be part of a walking corridor. And making sure that there were, as fewer delays and it was quick and easy for the pedestrians. This is what we've shown. We've shown kind of in this presentation, it's a very short period of time, kind of taking you through looking at how the detection worked, looking at the type of pedestrian metrics we then caught, and then how we used that. How that was used by the optimizer to facilitate the crossing. I just now quickly want to hand over to Dan about next steps.
I will be really quick, and I think just to say, it looks like the results are really promising. We do an independent verification, and we're now looking and working with our signals colleagues at other crossings, different types of crossings, so that we can expand the trial and pilot. Thanks.
And this has got nothing to do with our presentation, but I'm just putting it up there for information. Thank you very much.
Thank you, Andrew. I think you guys get the award for how much you've absolutely crammed into that. So if we've got any questions, one thing I would say is please do make sure that you speak to some of our speakers during the lunch break, because there is a lot of detail that they're just simply not able to get across in 15 minutes. So again, kudos for getting as much as you have done in that time. Do we have any questions for any of the presenters, Andrew and others? Oh, brilliant. Don't be too long, John.
No, I was just going to say, obviously we've watched this grow over time because you've shown us the way that this sort of technology works with your virtual actors and all this sort of thing. It's been nice to follow the journey and see it come through now to trials. What I hadn't picked up on before was the fact that, and I don't think you mentioned it before, I'm fascinated by this idea that your optimizer will actually suppress the demand and platoon the pedestrians. Yeah. Have I got that right?
Yeah, that's
so
exactly
basically
right.
If it says, well, there are so many pedestrians here now, but there's a lot more on the way, so what we're going to do is going to wait until we get here before we give them a green light.
Exactly.
All right. Next time I use one of the crossings, I've got yours on, I'm looking on my shoulder and thinking I better get running. So, no, a fascinating idea. It's something that would never really occurred to me.
So our detection has replaced the 3 existing detectors, but also added pavement users. So hence we're able to see what's coming down the pavement and then do the prediction of how many of them will turn into crosses, and then that leads into the optimizer doing its work.
So if you could get pedestrians with indicators on, that'd make your job even easier. Thank you for that.
Thanks, John. Do we have any questions? Ah, yes, we've got 2, one behind each other. I'll take the gentleman that's closest to the stage first.
Hi, Dan Huntshaw, Transport for London. I just wanted to check then. So you'd be able to use the data you could collect the data from these sensors and maybe use that as inputs for like pedestrian modelling and
yes.
other kind of activities, right?
Exactly. So it's the kernel of our technology, our software stack, which is kind of extracting behavioural analytics and data from the actors that we detect.
Okay, so
and then be able to report it.
Routing as well through routing would be through the
We don't do kind of journey times or kind of follow individuals around.
Right.
It's more being able to report on what the behaviour that we see from individuals and report it.
All right, well, that's valuable. Thank you.
Sorry, I'll just add, we do that because we have a pedestrian and vehicle classification system.
Yeah, Chris Bluck, TfL. Just a question to follow on John's point about suppressing the demand for the pedestrian until I think you said it was a critical threshold. So what's the default if the pedestrians never reach that, if you said to suppress the demand and say the number of pedestrians you think crossing don't cross or people cross against the red man, and so you don't hit that critical threshold, is there like a time frame to which you would then say, okay, don't worry about the critical threshold, just give that demand, or?
Yeah, absolutely. So there's timers involved, so there's only a certain amount of time that we can suppress the demand. And basically we can just cancel the suppression, it'll just go back to normal and just continue doing its thing.
Perfect, thank you.
Do we have any more questions? No, again, I would urge you to come and speak to these guys because the fact that you've tried to cram in so much is pretty incredible. Really.
We have a lot of data that we're more than happy to talk to you extensively about.